Strainers are elements very similar to filters, however, are ordinarily designed to exclude only large particles, generally 50 microns and above. Strainers are basically wire mesh fittings which offer less resistance to flow than a regular filter. Strainers and filters work in combination by allowing the strainer to remove any large contaminants that may easily clog the filter and letting the filter handle all those smaller particles the strainer fails to catch. Strainers can often be found on pump inlets as well as filler ports to reservoirs. Strainers are often sized using mesh count, where mesh count is the number of threads per inch. For example, a 200 mesh strainer has 200 horizontal threads and 200 vertical threads in a square inch. Strainers with higher mesh counts have more threads, thus smaller holes, and can exclude smaller particles. Strainers can sometimes be periodically cleaned and reused, whereas used filter elements are ordinarily discarded after reaching their time in service or becoming clogged. Speaking of clogged filters, most return filters include a clogged filter bypass and indicator. The clogged filter bypass is essentially a check valve with a light biasing spring, such that a fresh filter does not restrict flow and the bypass remains closed. If, however, the filter becomes clogged, a pressure differential develops across the clogged filter and the bypass opens, allowing the system to temporarily function without filtration. The bypass indicator warns an operator bypass has occurred, and it is incumbent upon any operator to initiate an orderly shutdown. A system operated for any length of time without the proper level of filtration is simply asking for trouble. Filtration can occur in several different places, notably return filters, suction filters, pressure or inline filters, kidney loop or offline filters, and filter carts. The most common filter location is the return line back to the tank, since it does not have any special pressure requirements. Any fluid routed through the system must go through the return filter at low pressure prior to being emptied into the reservoir. The fluid in the reservoir is then allowed a chance to cool, settle out any remaining particles, and dissipate any entrained air before it is pumped back into the system. We'll examine reservoirs, a necessary component in hydraulic power units, in a later lecture. Return filters, as the name implies, filter oil returning to the tank. A suction filter, sometimes called an inlet or sump strainer, in contrast, filters oil prior to it being introduced into the system by the pump. Suction filters must be designed to work at vacuum conditions, since they are in the pump's suction line. Suction lines, by the way, must be designed to withstand vacuum conditions and not collapse inward. For this reason, suction lines often include rigid reinforcements that allow them to remain open. A pressure or inline filter, in contrast, is a filter above stream of any valve or component in the system exposed to pressure. Pressure filters must be robust enough to handle these increased working conditions and are often used to protect special purpose components necessitating special filtration requirements. An example might be some stuck-up hoity-toity valve that has no fondness for the dirty oil enjoyed by the rest of the common rabble. No, ordinarily filters are meant to be unidirectional, since running a filter in reverse would blow out any previously entrapped contaminants and run counter to its intended purpose of cleaning the oil. This pressure or inline filter on the pressure line leading to the directional control valve would be unidirectional. Pressure or inline filters installed in bidirectional flow paths ordinarily use an arrangement of check valves such that incoming fluid is always routed in to out as intended regardless of direction of flow. This is one of the check valve applications I alluded to in the check valves lecture, available at the Big Bad Tech channel. A pressure or inline filter on the actuator side of the directional control valve would necessarily be bidirectional in nature. During extension, the arrangement of check valves ensures flow through the filter is routed in to out as intended. Similarly, during retraction, the arrangement of check valves ensures flow through the filter is routed in to out as intended. Kidney loop or offline filters are those filters that do not serve the main system, but rather filter fluid directly from the reservoir and back. A kidney loop filter often necessitates a small pump rated for low pressure to drive the kidney loop circuit. A kidney loop is in effect an isolated subsystem of a larger system that is tasked with fluid maintenance. The kidney loop circuit can periodically run the oil in the reservoir through the filter, thereby making use of idle time to perform regular maintenance. In addition to filtration, simply by keeping oil circulating, Kidney loops are sometimes used to warm up cool fluid in extreme cold conditions, ensuring its viscosity remains inside a desired range. Note that sometimes the main pump and return filter can also be used to perform kidney loop filtration with the help of an additional directional control valve. If this system experienced a lengthy idle time in the closed position and called for routine kidney filtration, the additional directional control valve could be shifted to the open position and the main pump turned on. The main pump therefore serves to filter the oil in the reservoir while on standby. If this system is called into service, the directional control valve closes and the return filter now filters oil returning to the reservoir. Finally, filtration can occur external to a system with the use of something called a filter cart. A filter cart or portable filtration unit is a special purpose device used to transfer fluid from a storage container to a reservoir, as well as perform thorough filtration that would ordinarily be cost prohibitive if included in a regular system. A filter cart is essentially a portable pump and a filter or filters. A filter cart can be used to fill a new system, empty an old system, change old fluid, or filter existing fluid. Moving on, oil employed in a hydraulic system has formal cleanliness standards established by the International Standards Organization. For applications necessitating extreme cleanliness, it makes sense to start with the cleanest oil available, whereas those applications not necessitating extreme cleanliness can get by with a cheaper, less clean oil. Hydraulic oil ISO cleanliness standards are communicated using a 3-number code, sometimes 2, where each number in the code represents a range of particles of a given size per unit volume. These 3 numbers respectively represent particles greater than 4 microns but less than 6 microns, particles greater than 6 microns but less than 14 microns, and finally particles greater than or equal to 14 microns. Each number represents a range of permissible particles of a given size per unit volume. For example, this directional control valve datasheet is expressly calling for oil with an 18, 16, 13 cleanliness rating. This means anywhere is from 1,300 up to 2,500 particles greater than 4 microns but less than 6 microns are present per milliliter, anywhere from 320 up to 640 particles greater than 6 microns but less than 14 microns are present per milliliter, and anywhere from 40 up to 80 particles greater than or equal to 14 microns are present per milliliter. If the data sheet says a particular component necessitates an oil with a 2-number ISO cleanliness code, it ordinarily means ignore particles less than or equal to 4 microns and concentrate on the 6 and 14 micron bin. For example, if this directional control valve didn't care about particles less than or equal to 4 microns, it'd be calling for 16, 13 oil. Finer applications like servo valves might call for oil with higher cleanliness standards. For example, a servo valve might call for oil using the 16, 14, 11 ISO cleanliness standard. This means anywhere from 320 up to 640 particles greater than 4 microns but less than 6 microns are present per milliliter, anywhere from 80 up to 160 particles greater than 6 microns but less than 14 microns are present per milliliter, and anywhere from 10 up to 20 particles greater than or equal to 14 microns are present per milliliter. Note the lower bin numbers indicate less particles of a given size per unit volume because the oil is cleaner. Higher cleanliness standards, by the way, goes hand in hand with higher costs and more intense maintenance. You should be able to use an ISO cleanliness chart and oil requirement to determine the number of particles of a given size for a particular oil. Finally, in addition to filtration, oil often needs to be conditioned to ensure it stays inside a given temperature range. Excessively cold oil is too viscous to pump, whereas excessively hot oil is too thin, leaks more, provides less sealing and lubrication, and runs the risk of damaging the oil's molecular structure. Conditioning tasks designed to keep oil inside a given temperature range are performed by heat exchangers, heaters and coolers. A heater adds heat energy to a system, therefore its arrows point inwards. A cooler removes heat energy from a system, therefore its arrows point outwards. As demonstrated previously, sometimes the simple act of keeping fluid circulating, equivalent to doing a couple jumping jacks or squat thrusts instead of building a fire, can keep the oil warm enough during lengthy idle periods thereby saving the necessity of incorporating an active heater. This being said, extreme environmentally demanding conditions may necessitate heaters. Coolers employing heat transfer fluids must circulate the oil to be cooled and the heat transfer fluid in opposite directions. A tube and shell heat exchanger employing a liquid heat transfer fluid is essentially a tube containing the oil to be cooled, jacketed by a shell containing the heat transfer liquid. Warm heat transfer liquid leaving the heat exchanger is still cooler than hot oil entering, as is warm oil leaving the heat exchanger hotter than the cold heat transfer liquid entering. This counterflow arrangement ensures heat transfer occurs the length of the heat exchanger. Baffle heat exchangers are like twisted up versions of a tube and shell heat exchanger designed to save space. A baffle heat exchanger is basically an alternating stack of oil and heat transfer liquid layers, where again oil and heat transfer fluid are run counter to each other to ensure heat transfer occurs the length of the baffle heat exchanger. Finally, note that the reservoir itself can be considered a fluid conditioning apparatus. Not only does the reservoir ensure a quantity of oil is readily available to the system, it also serves to cool liquid returning from the system and allow time for any particles to settle out and any entrained air to dissipate before the oil is again pumped up and circulated through the system. We'll examine reservoirs and hydraulic power units in greater detail in later lectures. Alright, that is that. In conclusion, this lecture discussed fluid contaminants, filtration, and conditioning. We defined contamination and contaminant sizing, identified sources of contaminants and discussed means of preventing contamination, means of filtering out contaminants, common filter performance ratings, including beta ratio, common filter locations, including return filters, suction filters, pressure or inline filters, kidney loop or offline filters, and filter carts, oil cleanliness standards, and fluid conditioning and heat exchangers. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.